Today we discuss about the generation recombination and high injection effects. For silicon and gallium arsenide p-n junctions, the ideal equation can give only qualitative agreement because of the generation and recombination of carriers in the depletion region. If we consider the reverse bias condition first, under reverse bias, carrier concentrations in the depletion region fall below their equilibrium concentrations. The dominant generation recombination process are those of electron and hole emissions through band gap generation recombination centers. The capture processes are not important because their rates are proportional to the concentration of free carriers, which is very small in the reverse biased depletion region. Two emission processes operate steady state by alternating emitting electrons and holes. The rate of electron hole pair generation can be obtained as shown in this equation, with the conditions that Pn is very much less than Ni and Nn is very much less than Ni. So we have the rate of generation is equal to minus u. We can write it in brackets sigma p sigma n V thermal into Nt divided by sigma n exponential in brackets E F minus Ei bracket close divided by Kt plus sigma p exponential in brackets Ei minus Et divided by Kt bracket close, the whole thing multiplied by Ni. So this boils down to, this is equal to Ni by tau g, where tau g is the generation lifetime, is the reciprocal of the expression of the square brackets. We can derive an important conclusion about the electron hole generation from this expression. If we consider a simple case where sigma n is equal to sigma p is equal to sigma o, in this case the equation will now reduce to this equation, that is G is equal to sigma 0 V thermal Nt Ni divided by 2 cos of hyperbolic Et minus Ei divided by Kt. The generation rate reaches a maximum value at Et is equal to Ei and falls off exponentially as Et moves in either direction away from the middle of the band gap. Thus only for those centers with an energy level of Et near the intrinsic Fermi level, this can contribute significantly to the generation rate. The current due to generation in the depletion region, that is J generation, is given by, this is equal to the integral of Qg dx. If we integrate it from 0 to w, this is nearly equal to Qgw, this is equal to Qniw by tau g, where w is the depletion layer width. The total reverse current for P plus N junction, that is for Na is very much greater than Nd and for Vr is greater than 3 Kt by Q. This can be approximated by the sum of both the diffusion current in the neutral region and generation current in the depletion region. So Jr is nearly equal to Q under root of dP divided by tau p Ni square divided by Nt plus Q Niw by tau g. For semiconductors with large values of Ni such as germanium, the diffusion current dominates at room temperature and the reverse current follows the ideal diode equation. But if Ni is small, for as for silicon and for gallium arsenide, the generation rate in the depletion layer may dominate. So we have, for under forward bias conditions, the concentration of both electrons and holes exceed their equilibrium values. The carriers will attempt to return to their equilibrium values by recombination. Therefore, the dominant generation recombination process in the depletion region are the capture processes. So we have P and Nn is nearly equal to Pn0 Nn0 Q e to the power Qv by Kt, that is equal to Ni square e to the power Qv by Kt, as we have shown over here in this equation. So if we substitute this in equation, so we and assume that sigma n is equal to sigma p is equal to sigma 0, then we have u is equal to sigma 0 Vth Nt Ni square in brackets e to the power Qv by Kt minus 1 bracket close divided by Nn plus Pn plus 2 Ni cos hyperbolic Ei minus Et by Kt, as you have shown in this equation. In either recombination or generation, the most effective centers are those located near the Ei. As practical examples, gold and copper yield effective generation recombination centers in silicon where the values of Et minus Ei are 0.02 volts for gold and minus 0.02 electron volts for copper. In gallium arsenide, chromium gives an effective center with an Et minus Ei value of 0.08 electron volt. So this equation will be simplified for the case Et is nearly equal to Ei. So the value of u will be equal to sigma 0 VTH NT Ni square e to the power QV by KT minus 1 divided by Nn plus Pn plus 2 Ni. So for a given forward bias, u reaches its maximum value at a location in the depletion region, either where the denominator Nn plus Pn plus 2 Ni is a minimum, or where the sum of the electron and hole concentrations Nn plus Pn is at its minimum value. Since the product of these concentrations is a constant, the condition, if we differentiate d Pn plus Nn, this is equal to 0, leads to dPn is equal to minus dn, this is equal to Pn Nn by Pn square, so into dP. So we have Pn is equal to Nn, as this is the condition for the minimum. This condition exists at the location in the depletion region where EI is halfway between EFP and EFN, as it is illustrated in this figure. So Pn is equal to Nn is equal to Ni e to the power QV by 2 kT. Therefore Umax is equal to sigma 0 V thermal Nt Ni square in brackets e to the power QV by KT minus 1 bracket close divided by 2 Ni in brackets e to the power QV by 2 kT plus 1. And so for V greater than 3 kT by Q, Umax is equal to half sigma 0 V thermal Nt Ni e to the power QV by 2 kT. So the recombination current then becomes equal to integral of Q U dx. The limits are from 0 to W. So this is nearly equal to QW by 2 sigma 0 VTH NT Ni e to the power QV by 2 kT. This is equal to QW Ni divided by 2 tau R e to the power QV by 2 kT, as we have shown in this equation, where tau R is the effective recombination lifetime given by, this is equal to 1 by sigma 0 V thermal NT. The total forward current can be approximated by the sum of this equation. And so for Pn0 is very much greater than Np0 and V is greater than 3 kT by Q, we have Jf is equal to Q under root of dP by tau p Ni square Nd e to the power QV by kT plus QW Ni divided by 2 tau R e to the power QV by 2 kT. In general, the experimental results can be represented by Jf is nearly equal to exponential QV by eta kT. Here the factor eta is called the ideality factor, where the ideal diffusion current dominates, eta is equal to 1, whereas the recombination current dominates, eta equal to 2. When both currents are comparable, eta has a value between 1 and 2. This figure shows an forward characteristic of silicon and gallium arsenide p-n junction at room temperature. At low current values, recombination current dominates and eta is equal to 2. At higher current levels, the diffusion current dominates and eta approaches 1. At even higher current values, we notice that the current departs from the ideal eta is equal to 1 situation and increases more gradually with forward voltage. This phenomena is associated with two effects: series resistance and high injection. We first consider the series resistance effect. As both low and medium current levels, the IR drops across the neutral region is usually small compared with KT by Q, that is of the order of 26 millivolts at 300 Kelvin, where I is the forward current and R is the series resistance. For example, for a silicon diode with R is equal to 1.5 ohms, the IR drops at 1 milliamperes is only 1.5 millivolts. However, for at 100 milliamperes, the IR drop becomes 0.15 volts, which is 6 times KT by Q. This IR drop reduces the bias across the depletion region. Therefore, the current becomes nearly equal to I is equal to IS exponential in brackets Q in brackets V minus IR bracket close divided by KT bracket close. So this is equal to IS exponential e to the power QV by KT divided by exponential of QIR divided by KT, and the ideal diffusion factor is reduced by a factor of exponential QIR by KT. At high current densities, the injected minority carrier density is comparable to the majority carrier concentration. That is, the N side of the junction Pn is where x is equal to xn, that is nearly equal to nn. This is the high injection condition. By substituting the high injection condition, we obtain Pn at x is equal to xn is equal to Na exponential qV by 2 kt. Using this as a boundary condition, the current becomes roughly proportional to exponential qV by 2 kt. Thus, the current increases at a slower rate under the high injection condition. Thank you.